Hi all. Today we are going to discuss different types of voltage to current converters using Opamp. In our earlier classes we have discussed a non-inverting amplifier and an inverting amplifier. Actually, these two circuits are converting the applied voltage into a current, applied voltage into a current. In your non-inverting amplifier, the current I is applied by the op-amp and that current is equal to the current flowing through the input resistance. Virtually, this will be at V potential, so V minus 0 by R, that is V upon R. Current flows through R. The same current has to flow through the resistance connected in between output and inverting terminals of the pack. So that current I is actually independent of the feedback resistance. So irrespective of this resistance, current flowing through this resistance will be always I, that's equal to V upon R. So we'll say that the current flowing through the resistance inserted between these two terminals is always depends on voltage V and its value is given by V upon R. So this circuit converts the input voltage into an output current. In the second case, similar to our non-inverting amplifier, this is an inverting amplifier. This potential is at 0 volts. Virtually they are at same potential. The current flowing through R is nothing but V minus 0 by R, that is V upon R. And as there is no input current from the op-amp, there is no input current into the op-amp inverting terminal, the same current I flows through the resistance connected in between output node and an inverting input terminal. So that current is nothing but I equal to V by R. That current is actually independent of the resistance connected here in between inverting node and output node of the pump. So this circuit is also converting the applied input voltage into a current. In the second case, op-amp sinks the current IV upon R, whereas in the first case, op-amp supplies the current I that's equal to V upon R. The problem with these two circuits is that the load is inserted between these two terminals and none of these terminals are at a reference node or a positive as well as negative feedbacks. So as shown, output is connected to inverting input and non-inverting input. And as we discussed in our earlier classes, V plus will be equal to V minus if negative feedback is dominating in the circuit. Here we have two different feedback, positive and negative. So let us identify the feedback signal available at V minus. Since equal resistors, the output voltage divides equally between these two resistors. So V minus will be dropped across R, that will be equal to V out by 2. Implies V minus is equal to V upon 2, implies we have a 50% negative feedback. While identifying the feedback at positive node, feedback implies the amount of signal fed back to the input side, and that signal should be proportional to only the output. But here in the circuit we have an independent source. This independent source also will influence the potential here. So while identifying the percentage of feedback available at the positive input, we should nullify the effect of independent sources present in the circuit. So this is a voltage source. To nullify the effect of a voltage source, we have to short its terminals. So I am grounding it. So at present we have output signal and we have to identify V plus. The moment I am grounding this terminal, this R and RL are in parallel. So R and RL are in parallel, right? So that parallel combination is series with your R connected to the output side. So you can write V plus equal to V out multiplied by R parallel RL, this equivalent resistance, upon R plus R parallel RL, right? So R parallel RL will be always less than R. So V minus was equal to V by 2. So here V plus will be anyway less than V minus, right? So if we are taking all these resistors as 1 kilo ohms, so 1 parallel 1 will give you V plus equal to V out multiplied by 1 parallel 1, R equal to 1, RL equal to 1, this RL is equal to 1. So R parallel RL will give you 1 by 2 kilo ohms divided by R is 1, R is 1, 1 parallel 1, again 1 by 2 kilo ohms. So that will give you V plus is equal to V out by 3. So as this comes in parallel, so always in this circuit V plus will be less than V minus, implies negative feedback dominates, so V plus equal to V minus, right? So we'll make use of this expression while evaluating the output voltage and the current flowing through the load RL connected in between positive input and ground. So compared to earlier circuit, the load RL is appearing between a particular node and a reference node or a ground node, right? So here we have to identify the expression of current IL, and it will be independent of RL, implies irrespective of the load connected between positive input and a ground, the current flowing through that load or IL will be independent of the load resistance, and in this circuit IL will be equal to Vs upon R. Vs is this voltage source and R is this resistance. Let us see how Vs by R is equal to the current flowing through the resistance RL. Right, so while analyzing the circuit, I should connect my independent source back in form. Then we have to identify IL, and H will be independent of RL. Let us see that. Right. So V plus equal V minus, negative feedback. So output is always in between plus or minus VCC. So it's a linear circuit. This signal is at V out by 2. V plus equal to V minus is valid because negative feedback is dominated in the circuit. So here we'll have same signal V minus, that is equal to V out by 2. So if this current is my IL, then I can easily write, if this is I1 and this is I2, my IL will be equal to the sum of I1 plus I2 as per Kirchhoff current law. Sum of this and this will flow through RL, that's equal to IL. And I1 is nothing but V out minus this potential is V out by 2 divided by R. So this is nothing but output voltage minus V plus, that is nothing but V out upon 2 divided by R plus. My I2 is marked in this direction towards right. So that's equal to Vs minus Vs minus V out upon 2 divided by R. Right? So V out minus V out by 2 will be V out upon 2 and 2R plus Vs by R minus V out by twice of R. From this expression, it is clear that this term and this term will cancel each other. So my IL will be equal to Vs upon R. So my IL is independent of RL. So if we are inserting any value here, the current IL will be always Vs upon R. The resistance is this R. Right? And you can see that that is happening because this cross product and this cross product are matching in this circuit. So in any circuit, in this configuration, if these cross products are matching, the current IL, you can directly write it as voltage applied at positive input side upon the resistance R. The resistance connected at the non-inverting input in series with the input DC source. Right? Let us evaluate the corresponding output voltage. While evaluating the output voltage, you can see that V out is this node voltage with respect to ground. So that is the sum of this drop plus this drop. So I1R plus IL into RL. So V out is nothing but, as per KVL, voltage across R, that is I1 times R plus IL times RL. The value of I1 was nothing but V out minus V out by 2 by R, that was equal to V out by 2R multiplied by R plus IL multiplied by R. IL was Vs upon R multiplied by RL. So this will get cancelled. So V out minus V out by 2 will give you V out by 2 on left hand side. That's equal to Vs upon R multiplied by RL. That implies V out is equal to Vs times RL upon R. So this circuit will produce an output voltage that is equivalent to this and a load current IL that is independent of RL. Its value is nothing but Vs upon R. Right? And always, if these cross products are matching, without doing any analysis, you can directly write the current IL is nothing but equal to Vs upon this resistance R. Right? So, irrespective of the value of resistance inserted between V plus and ground, current will be always Vs by R, and two extreme conditions are excluded. That is, if RL equal to 0, this expression is not valid. If RL is equal to infinity, then also this expression is not valid. Right? And of course, the output of the op-amp should not saturate. Output voltage should not saturate, as well as output current also should not saturate. Op-amp should have a flexibility to vary its own output voltage and current so that this current flowing through RL is independent of RL and its value is equal to Vs by R, and corresponding output voltage is nothing but Vs RL upon R, right? Let us modify this circuit slightly. So we have another one. Initially Vs was connected here, so that Vs I am moving to inverting side. All other parameters are same. And in this case also, as we discussed earlier, these two are in parallel. So V plus will be always less than V minus. So negative feedback will be dominating in the circuit. So this will be V out by 2 if you are grounding Vs source, and V plus will be always less than that because these two are in parallel. So negative feedback dominates, V plus equal to V minus is valid, right? So we will move our derivations based on V plus equal to V minus conditions, right? So let us see what will be the expression for IL. To identify that, we have to identify V plus or V minus first. This is my V minus. Equal resistors to sources. So V minus voltage at inverting input, V minus will be equal to Vs by 2 plus V out by 2. Both voltages divides equally between resistors. Or this is equivalent to Vs plus V out upon 2, right? And of course V plus is also equal to the same value Vs plus V out upon 2. So if my current directions are I2 leaving this node and I1 coming to that node, then I can directly write my IL is equal to the difference between I1 and I2. I1 minus I2. And my I1 is nothing but potential difference is V out, and this is at Vs plus V out by 2. So V out minus V out plus Vs upon 2 divided by R minus the second term I2 is nothing but this current Vs plus V out by 2 minus 0 by R. So Vs plus V out by 2 divided by R. So rearranging this term, 2V out minus V out, 2V out minus V out minus Vs divided by 2R minus Vs plus V out by 2R is the current IL, right? So 2V out minus V out will be V out minus Vs upon twice of R minus inside the bracket V out by twice of R. It is clear that this minus term, V out term will cancel each other. This will cancel each other, positive and negative. Then minus Vs by 2R minus Vs by 2R will become 2 times of minus Vs by 2R, that is nothing but minus Vs by R. That is my IL. So if your source is moved to the inverting input side from non-inverting terminal, then there is an inversion in the load current. So actual load current Vs by R is moving towards up. So IL in this direction is negative. That's equal to minus Vs by R. So here also the cross product is matching each other. And for this kind of circuit with the Vs connected to the negative input side, You can directly write IL as this voltage Vs divided by R. That value of R is the same resistance as earlier, right? Not this resistance, right? The confusion regarding the resistance value will be clear by discussing after discussing next problem. So let us identify the output voltage of the given circuit. So this circuit is also acting as a constant current source circuit. You can insert any value between these two nodes. Then irrespective of that resistance, the current IL will be always Vs divided by R with a negative sign. And the two extreme cases are excluded, RL equal to infinity and RL equal to 0 in our discussion. Also, output should not saturate, output voltage should not saturate, as well as output current also should not saturate. Opamp should have a flexibility to change its own output voltage and output current so that this current IL is independent of RL and is equal to minus Vs by R. Now let us identify the output voltage quickly, right? So we know that V plus is nothing but Vs plus V out by 2, and that should be equal to the drop across RL with respect to ground. So you can equate that V plus Vs plus V out by 2, that should be equal to IL multiplied by RL. So Vs plus V out is equal to 2 times IL RL. Vs plus V out is equal to IL value we evaluated as minus Vs upon R. So minus 2 Vs upon R multiplied by RL. So taking Vs to the right hand side, V out is equal to minus of 1 plus 2 RL upon R. So my output voltage is nothing but V out is equal to, it's negative because your input is connected to the inverting input of your Opamp. So V out is equal to minus of 1 plus 2 times RL upon R. So as we discussed, if these cross products are matching, IL directly equal to source by this resistance with a negative sign in this case, whereas in the earlier case, the same voltage was Vs divided by the same resistance here Vs upon R, but sign is positive. And output also was positive because your input is connected to the positive input of your op-amp. The confusion regarding the resistance, this R or this R will be clarified after discussion of next problem. Right, here we have two different circuit corresponding to our last two cases. Here we have 2 volts here, and this cross product is 8, this is also 8, so they are matching. So directly you can write IL is equal to nothing but 2 divided by 2K, that is 1 milliampere. Right, to clarify that, let us evaluate the actual value of IL, then we'll check whether that will be equal to 1 ampere or not. It's quite simple to identify. Let us see that. Since this is V out, my V minus will be equal to V out into 1 divided by 4 plus 1, that is V out by 5. V out divides between 1K and 4K. So negative feedback dominates in the circuit as we discussed. Then my V plus also should be equal to V out by 5, right? So my IL is nothing but sum of these two currents. Let me mark it as I1 and I2. So IL is nothing but I1 plus I2. IL is equal to my I1 is nothing but V out minus V out upon 5 divided by 8K. I2 is nothing but 2 volts minus V out upon 5 divided by 2K, right? Evaluating the value of IL. So taking the LCM, I'm making it as milliampere by cancelling kilo ohm in the denominator. So IL is equal to V out minus V out by 5. Taking the LCM, 5 V out minus V out, nothing but 4 V out upon 40 plus 10 minus V out by 10, that much milliampere, because km 1 over km taking it as 10 power minus 3. So 4 V out by 40 will be V out by 10, and this V out by 10 and a second term in the expression will get cancelled. The remaining 10 is 10 by 10, that is nothing but 1 milliampere. That is nothing but 2 upon 2k, that's equal to 1 milliampere. Similarly, the output also can be obtained by taking these two drops, adding together, or equating IL with a V out by 5. So IL was 1 milliampere. If RL is in kilo ohms, 1 milliampere into RL, that is IL RL will be equal to V out upon 5. IL is 1 milli. If RL is in kilo ohms, we'll get V out is nothing but 5 times RL. So depending on the value of RL, your output will vary, and that output should be positive as expected. Let us look into the second case here. Second case also, the cross product is matching. 1k into 2k is equal to 4k into zero point 0.5 kilo ohm. So the cross products are matching each other, and the expected value of current IL is nothing but IL is equal to source is plus 1 volt and connected to inverting input, so minus 1 divided by this resistance as per our discussion, so that's equal to minus 1 milliampere. So let us see whether it is minus 1 milliampere or not. So to do that, let us evaluate V minus first. And if a negative feedback is dominated in the circuit, also if the Opamp is not saturated, then V plus will be equal to V minus. So V minus can be directly obtained as V minus is equal to two sources divides between 2k and 4k. So 1 into 2k divided by 6k. So 1 into 2 by 6 plus V out into 4 by 6. V out into 4 upon 6. So 2 plus 4 V out by 6. So your V minus is nothing but 2 plus V out 2 plus 4V out by 6. And that will appear as your V plus. So as we discussed earlier, IL is nothing but I1 minus I2. So IL is equal to I1 minus I2. The value of I1 is nothing but V out minus V plus divided by 0.5 K. V out minus V plus is equal to V minus, that's equal to 2 plus 4 V out by 6. 2 plus 4 V out upon 6 all divided by 0.5 K minus I2 is nothing but V plus minus 0 by 1K. V plus is nothing but 2 plus 4 V out by 6 multiplied by 1K in the denominator. That value will give you IL. Taking the LCM here, 0.5K is equivalent to 1 by 2. So this will become 6V out minus 2 plus 4V out upon 6 into 0.5 is nothing but 3 kilo minus 2 plus 4V out by 6K. That will give you, its value will be equal to, this will become 12V out. If I am multiplying with 2 in the numerator, this will be 12V out. This will become 6K. This will become 4. This will become 8V out. So 12V out minus 8V out will be 4V out. 4V out and this 4V out will get cancelled. Then remaining terms are minus 4 by 6, minus 2 by 6. So that will be equal to minus 4 by 6K minus 2 by 6K. That's equal to minus of minus 6 by 6K minus 6 by 6K, the positive sign. So that is nothing but minus 1 milliampere. As expected, 1 volt divided by 1K is 1 milliampere. So 6K upon 6 upon 6K is nothing but 1 milliampere, and there is a negative sign. So as expected, the current is nothing but minus 1 milliamperes. The output voltage can be evaluated by taking the voltage drop across these two. The output voltage V out can be easily identified by equating V plus and V minus. The current IL, we got it as minus 1 milliamperes. So minus 1 milliamperes multiplied by RL will give you V plus, and that should be equal to V minus. V minus is nothing but 2 by 6 plus 2 by 6 plus 4 V out by 6. If RL is in kilo ohms minus RL minus 2 by 6 will give you 4 V out by 6. That implies V out is equal to minus 6 RL minus 2 divided by 4. So depending on RL, we'll have different V out. The current is always minus 1 milliampere independent of the resistance RL except two extreme cases R equal to 0 and infinity. And of course these cross products are matching. So directly you can write it as 1 by 1k with a negative sign because your input is applied to the negative side compared to the earlier case. That's all about the constant current source with a floating load and a grounded node. Thank you.